Hello, AP Chem. We are going to be talking about specific heat today. We have talked about heat. We've kind of talked about enthalpy a little bit, and now we're going to kind of get into more of the number crunching as it comes to one of the more, well-known equations in terms of thermodynamic calculations, and that is the Q equals MC delta T equation. So we'll be getting into that a little bit today, but first we actually have to talk about what the heck this specific heat thing is. So when we talk about different substances like water, air, metals, wood, whatever, all of those things change their temperatures at kind of a different rate than other things do. And so when we talk about how fast something changes temperature, it has to do with how much energy it takes to make that thing actually change a degree Celsius. And that is called the specific heat. So the specific heat is, by definition, the amount of energy required to raise the temperature of 1 gram of whatever that substance is by 1 degree Celsius. And that can be in the upward direction if you're adding heat, or in the downward direction if you're removing heat. So it's the amount of energy that it takes to take literally just 1 gram of that substance 1 degree Celsius in any direction. And so when we talk about specific heat, it is a property that's unique to each substance. It has its own identifiable specific heat, kind of like density. And it's one of the ways that you can actually figure out what an unidentified substance is if you can figure out its specific heat. It helps you narrow it down and you can figure out what chemical you have. Okay, so when we talk about specific heat values, here are a bunch of different examples. And the one you kind of always see at the top of the list for high specific heats is liquid water. Water in its liquid form has a very high specific heat, and it's much higher than a lot of different things, and its specific heat is 4.18 joules per gram degree Celsius. The units on your specific heat are joules per gram degree Celsius because it's how many joules it takes to move a gram 1 degree Celsius. So you've got the joules over grams degree Celsius. And the specific heat of water is really, really high. Like I said, it takes a lot of energy to get water to change its temperature. Even like ice has a lower specific heat than water does. So if you heat up ice, and we talked about this a little bit, steam too, it doesn't take as much energy to heat up ice and steam as it does to heat up liquid water. Liquid water's got kind of these amazing weird properties that make it a little bit more special compared to everything else. If you take a look at some other values on here, like for instance, liquid ethanol has a specific heat that's, just over half the value for liquid water. And so there are just some kind of unique properties that cause this. Now, metals tend to have lower specific heats and they heat up pretty quickly. So if you look at our metals here, aluminum has a specific heat of around 0.9, gold's around 0.12, silver is 0.23. And when you look at these values, the judgment call that you might have to make is like, which one of these things is going to heat up faster? And so if you think about a finite number of joules, like let's say 100 joules worth of energy, and you put that into the same mass, so let's say 5 grams of a bunch of different substances, and you put that into each of them, you are going to get different temperature changes for each of those substances based on how much their specific heat is or what value that is. So for instance, if I've got water here, it's going to not move as much because it takes 4 joules to make that 1 gram move a degree Celsius. So if I have 5 grams of stuff, it's going to take 20 joules to make 1 degree change. On the other hand, if I have, let's say, like iron here, iron has a specific heat of 0.449. So it's, on the, range of about 10 times less for its specific heat. So it's going to only take me, instead of 20 joules, it's going to take me around 2 joules to make that same temperature change for iron. So when we talk about specific heats, when you have things that have very big specific heats, they take a long time to heat up and a long time to cool down because you got to take a lot of energy out of them. And things that have lower specific heats heat up really fast and cool down really fast. And I would say the best example of this is our big, blue, beautiful neighbor, Lake Michigan. So Lake Michigan, having our school literally on the coastline here, it's cold here all the stinking time. Right? Like it's cold. It's always cooler by the lake in the summertime. And that's because the specific heat of water of Lake Michigan is so high that it takes a long time for Lake Michigan to heat up. And so on our first nice sunny day where it's 70 degrees here, that lake is maybe only 55 degrees because dirt has a much lower specific heat than the lake does. And so the lake takes a long time for that to heat up. And if you have a wind that blows over the lake, it takes that cool air and blows it over the land, right? Makes sense? The same thing, like if you've ever, in the wintertime, you might notice here where we get rain right along the lake shore, but that it's snow when you go like 5 miles out. That has to do with the water too. So the water also keeps us warm like a big wet blanket. When it's negative degrees outside, the water out there is still above the freezing point. And you might get some ice floating on the top, but it's very rare that you get Lake Michigan to freeze over. It's got to be really, really, really cold to make that happen. And it will never freeze deep. It's just not going to happen because there's so much water there. So being by the lake changes our climate here a lot because of water specific heat. And again, just remember that if you have a big specific heat, it takes a long time to heat up and cool down. And if you have a low specific heat, it takes not that much time. So the reason I have the water circled is because you guys are going to need to memorize the specific heat for liquid water. It's 4.18 joules per gram degree Celsius, and you need to remember that. Okay, so keep that in the lockbox there. I do not believe it's on your equation sheet either, so you're just going to need to know that value. So this is a good example I like to think of. We have a pot and we have some water. Let's say you're making some mac and cheese and you heat up the pot. So this specific heat here is in joules per kilogram per Kelvin, but basically it's 1 kilojoule per kilogram per Kelvin. That's the same as 1 joule per gram degree Celsius. So the pot itself, if you just want to heat the pot up, is going to heat up really fast. But if you are ever hungry and trying to make that mac and cheese, it feels like the water takes forever to heat up. It's because it heats up 4 times slower than the actual pot itself. So it takes a really long time to make water change its temperature. Okay. And again, if you're cooling it down, you got to take that out. If you're heating it up, you have to add that energy in. Now, the heat equation that we use to do calculations for specific heat and using specific heat is Q equals MC delta T. And I know for a fact that this guy is printed on your equation sheet. In this equation, Q is equal to heat, like we talked about before. So that answer is going to come out in joules every time. You may need to convert to kilojoules, but it's going to come out as joules when you use this equation, assuming you use the other variables that I have here. So M is mass, and if that's in grams, then that's what you're going to have. But the big variable here is the specific heat. Most of the time on the exam, they're going to be talking about the specific heat in joules per gram degree Celsius, which is why we use that. Once in a while, you'll see it reported in other units like you just saw in the previous slide. But for our cases, I think we'll be at joules per gram degree Celsius. And then delta T is change in temperature. Just like reading a burette, it is always final minus initial. And the sign that you get will be very important when you do certain calculations later on. So if you get a negative sign, that negative sign is going to be really important compared to a positive sign. So just be careful when you do that. It's always final minus initial. Okay, so we're going to actually do 2 example problems to see if you have any questions, and then we'll let you off and get to your homework. So the first example is going to be how many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 degrees Celsius to 55 degrees Celsius if the specific heat of aluminum is 0.9 joules per gram degree Celsius. Now, do I think they're going to put this type of question on the exam? Maybe not, but I think it's good for us to kind of go over the basics of how to use this equation before we get into the complicated aspects of the solution. So we got to kind of walk before we run with these. So that's what we will do. Alrighty, so example number 1. How do I know how to use this equation first of all? Well, it gives me a mass. The big tip off here is the delta T, the change in temperature. So I get a T final and a T initial. That lets me know I need to use my Q equals MC delta T equation, and it gives me my specific heat. So when I have this equation, Q equals MC delta T, you need to figure out what variables you have, and you don't have kind of like the ideal gas law. So I'm going to make a list here. My problem reads 10 grams of aluminum, so that's a mass. Okay. I've got a delta T here, and remember it's final minus initial, so it's 55 degrees Celsius minus 22 degrees Celsius. That's my delta T. And then my specific heat is 0.9. Units on that are joules per gram degree Celsius. And you'll see in just a minute why those units are really important. So I'm looking for my heat, how many joules of energy. So that is there. I've got my Q. And then I'm going to put these numbers in and plug and chug. So I've got 10 grams times my specific heat, 0.90 joules per gram degree Celsius, and then times my change in temperature, which was got to do that math, 33 degrees Celsius, and it's positive. Okay, so it's literally plugging and chugging, but I'll show you why the units are important here. So grams cancel out and degrees Celsius cancel out because of the units on our specific heat, and you are left with joules. So all I need to do is take 10 times 0.9 times 33 to get my answer, and that comes out to be 297 joules. If I wanted to convert this to kilojoules, I'm going to divide by 1,000, so it'd be 0.297 kilojoules. It's not that many joules, honestly. Like I said, it's not even 1 calorie worth of food. 1 calorie is 4.18 kilojoules. So it's not that much that actually is happening there. Okay? So that is how you do kind of your basic equation. Now, because this has a lot of variables, much like the ideal gas law, you can change the variable and then you'll solve for something else, which is what we'll do in example number 2 here. All right. So example number 2 says a 15-gram piece of cadmium metal absorbs 134 joules of heat while rising from 24 degrees Celsius to 62.7 degrees Celsius. Calculate the specific heat of cadmium. Now, information is here. I want you to pause the video, see if you can figure it out, and then we will go to our answer, okay? So give it a shot, and we'll talk in however long it takes you. All right. Coming back, solve this one, and you should be a profesh at dealing with these problems. Okay, so here's example 2. A 15-gram piece of cadmium metal absorbs 134 joules while rising from this temperature, and it's asking for the specific heat. Oh, and we got a mass here. So same equation, Q equals MC delta T. But in this case, as I'm reading through my problem, I've got my mass again. That's 15 grams. Okay. Now, read through. Now, it's telling me in this case that I'm absorbing 134 joules. So joules are my units for the Q. So I have my Q as 134 joules. Okay. And then look in here, I've got a final temperature and an initial temperature, so I can find my delta T. It's going to be 62.7 degrees Celsius minus 24 degrees Celsius, and that change is 38.7 degrees Celsius. And it says to find my specific heat, so I don't know what C is. So in this case, we're looking for C in this problem. Now, you know, if you've been following the videos, that I like to do the algebraic rearrangement first, and then I put the numbers in. So if I'm looking for C, I'm going to be dividing by M delta T. And then M cancels out, and I've got my C. So C is equal to Q over M delta T. And I've got Q, 134 joules, divided by my mass, 15 grams, and my change in temperature, which is 38.7 degrees Celsius. Okay, so When you type this into your calculator, you need to be careful because these two things here need to go in parentheses as you put them in, because otherwise your order of operations can get messed up and it's not great. So 134 joules divided by 15 times 38.7. And that's going to come out to be 0.23 joules per gram degree Celsius. And if you remember, the units on our specific heat are joules over grams degree Celsius. So none of these cancel out because this is the unit we want here. Now, a word for you. If you are doing problems like this and you have a negative delta T, it is not possible to get a negative C value, because that means that you would add energy and it would get colder, which is physically impossible. So when you get a negative delta T, you're probably going to have a negative Q value, and then those will cancel each other out. So, and again, this is just an example. If this were negative and this were negative, they would still cancel out to give me a positive specific heat. So just be aware of that as you go along, that you cannot possibly have a negative specific heat. It defies the laws of nature in this situation. Okay? So if you have any questions, please make sure you get them cleared up. Otherwise, it's time to go on to your homework, and I wish you luck, and we will talk to you later, okay?